Hello, everyone, and welcome to the July Link Tech Talk. My name is Olivia Lynn, and our co-host is Colin Orion Chandler. We're both members of Link Frameworks, I as a software developer at Carnegie Mellon University, and Colin as a project scientist at the Dirac Institute and the University of Washington. Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, here we highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analyses of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific, 1 p.m. Eastern. Our speaker today is Craig Pellegrino. Craig is currently a senior support scientist at NASA Goddard Space Flight Center. His background is in time domain astronomy, specifically focusing on observational studies of rare and unusual supernovae. In addition to his research, Craig is also involved in building software infrastructure for the time domain ecosystem. He's currently a member of the Across project at NASA, which builds software to better enable time domain observations using NASA's fleet. For the talk, please ask questions on Zoom or in the Link Tech Talks channel of the Discovery Alliance Slack. On Zoom, you can type questions into chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. With that, Craig, please take it away.
Okay, great. Thank you so much. Let me share my screen. Okay. Thank you so much, everyone, for being here, and thank you to the organizers for having me. So my name is Craig Pellegrino. I'm a support scientist at NASA Goddard, but today I'm actually going to be talking about work that I began as a postdoc at the University of Virginia and am still involved in today, and that's building this package called GOPREAUX, which is developing spectrophotometric templates for extragalactic transients using Gaussian process regression. So here's a brief outline of the talk I'll give today. I'm going to start with an introduction to the current state of time domain astronomy. Then I'll introduce GoPro. I'll talk about the sample and the data that we're working with. I'll give a brief introduction to what Gaussian process regression is and give an overview of our codebase. Then I'll demonstrate how we create some of these template models and how we can use them for predictions of different types of supernovae. I'll talk about how we're validating our templates now against other templates in the literature. And finally, I'll conclude with some future outlook and work to be done. So I like to start with an intro to time domain astronomy. So over the past decade or so, different time domain surveys such as ZTF, ATLAS, and ASSASSIN have discovered this exponentially increasing number of transients. So what I'm plotting here is the number of discovered transients in blue versus the number that have been spectroscopically classified in red. This is data taken from the Transient Name Server, or TNS, which is sort of this bookkeeping server for different extragalactic transients that are reported by the community. And this y-axis here is in log space. So you can see this exponential increase in the rate of discovery, whereas the rate of classifications has more or less plateaued in the last 5 years or so. And this really shows that we've entered this regime in which we're limited by the amount of spectroscopic follow-up resources that we can devote to classifying different transients that we discover. And of course, this problem is only going to get worse as we've officially reached now the start of LSST. So LSST will discover something like 200 supernovae or other extragalactic transients in each image that it takes. So if you multiply this by the number of images taken per night and the number of nights per year, LSST will discover upwards of 1 million or more transients each year. So this exponential increase that I showed in the previous slide is only going to continue while we still are stuck in this follow-up limited regime, where we're really limited by the amount of resources that we have to follow transients in more detail. And in particular, not only will LSST discover exponentially more transients, but because of its depth, it's going to push the discoveries out to higher redshifts. So shown here is a distribution or a predicted distribution of the redshifts at which LSST is going to discover supernovae. I think this is for type 1a supernovae, but you can see here for the different numbers of observations in different types of filters and the signal to noise ratio, the distribution here peaks at something like a redshift of 0.4 or 0.5. And so what this really means is that the vast majority of the supernovae that LSST will discover will already be too faint for typical ground-based follow-up. So this faintness at higher redshifts, combined with this exponential increase in the rate of discovery, means that we need to rely more on photometric classifications alone, as well as photometric predictions of typical supernova evolution, in order to identify the supernovae that we care about for our own scientific goals, whatever those may be. However, this is easier said than done. So a big reason for this is because at high redshift, the rest frame ultraviolet and optical emission of the supernovae gets redshifted into the observer frame, optical or near infrared. So shown here is a great visualization of this effect. The solid line on this plot is a spectrum of type 1a supernova at a redshift of 0.01, so very nearby. And that dashed line is the same spectrum redshifted to z equals zero point 0.5. And this is overlaid on top of the different LSST filter transmission curves. And so you can see that at low redshifts, the peak of this SED is somewhere in the U or the G band, but at higher redshifts, that peak gets redshifted out into the R band. So therefore, in order to photometrically classify or identify different types of supernovae from the LSST alert stream, we need to get a better handle on their rest frame behavior, as well as an understanding of how their full spectral energy distributions look like from the ultraviolet to the infrared. And this is really crucial to photometrically classifying these high redshift supernovae and identifying or inferring their physical properties from photometric data alone. However, to date, most modeling efforts of supernovae in the literature have been more or less on a filter by filter basis. And this is mostly because up until recently, we've really been limited by small sample sizes of objects that have really well sampled data sets, or different objects have more heterogeneous data. So, shown here on the right is sort of an example of what most of these models have looked like in the literature to date. We have different light curve templates in different filters. Those templates are all fit or generated more or less independently from one another. But this is ignoring sort of this crucial fact, which is that the flux across filters is actually interdependent. It's more or less the same physical processes that's producing G band flux as R band flux. So therefore, we really need to model across both filter and phase simultaneously. This will inform better modeling efforts because the flux in a very well sampled filter can then inform predictions in another filter where the coverage might be sparser. And we can obtain a better understanding of the full supernova SED. And this will allow for better predictions at high redshifts, again, where that SED gets redshifted from the ultraviolet to the optical and the infrared. So we've also entered this regime now where we have enough open source data from different time domain surveys, as well as different data releases from different collaborations, that we can actually start conducting these modeling efforts at the population level. So this is where this package called GOPREAUX comes in. So to create these better spectral energy distribution or SED models of different types of supernovae, we've developed this package called GOPREAUX. GOPREAUX is a bit of a tortured acronym. It stands for Gaussian Process Optimized Photometric Regression of Extragalactic Archival Ultraviolet to Infrared Explosions. A bit of a mouthful, but it essentially consists of three different parts. So first, we have this data repository where we have uniformly processed ultraviolet to infrared photometry that's all publicly accessible, covering about 1,300 different transients. Second, we have this open source code that will allow users to model this photometry that we've already processed across both phase and wavelength simultaneously using Gaussian process regression frameworks, which I'll cover a little bit later. And then finally, we have these final open source spectrophotometric templates, which are essentially these 3D spectral energy surfaces that can be used to predict things like different light curves, SEDs, photometry, or classify supernovae at any arbitrary phase, wavelength, or redshift. So for the remainder of this talk, I'll describe each of these features in a little bit more detail, and then give some examples of the different validations of the template models that we produce with GOPREAUX. So first, let me discuss the sample that we're working with. So we have about 1,300 transients in our sample, most of which are supernovae. So this little mermaid chart here shows the breakdown of how we've split up our supernova into different types and subtypes. This is mostly motivated by the fact that we're focusing internally on core collapse supernova subtypes. These are circled in black on this plot, and these consist of things like type 2, stripped envelope, superluminous, and type 2n supernovae. These all come from massive stars that were born with something like greater than 8 times the mass of the sun. We also have data for these mysterious class of objects called fast blue optical transients, or FBOTs. we've lumped in the type 1BN and type 1CN supernovae into this category because they tend to evolve on similar timescales. And then finally, we have this sort of catch-all other category for mostly non-core collapse supernovae, such as type 1A supernovae, as well as other types of transients like tidal disruption events or anything that's unclassified. So if you're a type 1A fan, I'm sorry that I've thrown your favorite supernovae into this other bin, but this is mostly to inform sort of our own internal modeling efforts. And all of the data for these type 1As are still processed and available if anyone's interested in working with them. So our sample is primarily driven by objects that have been observed by the Swift Observatory. And this is to really ensure that the objects that we're modeling have sufficient coverage in the ultraviolet. And again, this is because we're trying to build these spectrophotometric templates that extend all the way from the ultraviolet to the infrared to inform these modeling efforts of these high redshift supernovae. So this means that our objects are primarily low redshift or very bright supernovae because these are the ones that are more likely to have Swift observations. We also supplement these data with any other data that we can get our hands on, basically. So anything from open source data releases from different collaborations, different time domain surveys such as ZTF, Atlas, and Assassin, as well as other data sources such as the Open Supernova Catalog, which is this sort of open source repository of archival supernova data. All of the Swift and the time domain survey data has been uniformly processed as part of this campaign. So we've written custom data reduction pipelines to uniformly process all of these photometry in order to reduce biases in the actual data reduction steps. So all of these data have background subtraction applied to them at the pre-processing step to ensure that we're really fitting the flux of the supernova itself and not the background host galaxy as much as possible. We also require that all of the objects in our sample have a well-sampled light curve peak in the optical bands, and that's to ensure that we can fit for their time of peak and their peak brightness, because this is an important sort of normalization step in the modeling efforts, which I'll get to a little bit later. So the final results of all these cuts is a final sample of something like 1,300 transients, and this is one of the largest uniform modeling efforts to date. So this histogram on the right here shows the number of transients in our sample in orange compared to the total that have been classified on the transient name server in blue. And the percentage above each bar gives the percent overlap between our sample and the TNS total. So you can see that for most of the different subtypes, we maintain pretty good coverage overall of the TNS total. Most subtypes have 10 to 20% of the total TNS sample in our sample. This number goes up a little bit more for the rarer types of supernovae, like these F-bots and these superluminous supernovae, which tend to be more prioritized for ground-based and space-based follow-up. And these type 1A supernovae have less coverage overall. However, there's just more of them in general. And also, they tend to be UV dim, so they aren't as prioritized for Swift observations in general. So across these 1,300 transients, we've aggregated close to 146,000 different data points. So this distribution is shown here on the right. This gives the total number of observations by phase broken down into different subtypes of supernovae. You can see that, not surprisingly, the densest observations tend to be clustered around peak brightness, because again, this is when the supernova is brightest. We also have the most observations for the more common types of supernovae, such as the type 2s and the type 1As. But we also have pretty good coverage overall of all different types of supernovae. And this coverage extends out across a wide range of phases. So we have observations starting something like -50 to -30 days, especially for the longer-lived supernovae, like superluminous supernovae. And these extend out to 100 to 200 days after peak brightness. And this phase coverage is really crucial to capturing the full evolution from very early to very late times of these different supernova types. This is a similar plot, but these are instead violin plots now, which show the distribution of the observations in each filter as a function of phase. So the width of each violin here corresponds to the density of observations at that phase for that filter. And given to the sort of left vertically along each violin is the number of observations that we have in that filter across all of the different supernova subtypes. Again, you can see that our coverage is really good around peak brightness, not very surprising. But maybe more surprising is that we actually have very good UV coverage starting something like -30 days before explosion, extending out to maybe 100 days after explosion. The coverage gets even better in the redder bands. This is because supernovae tend to be longer lived and slower evolving in the redder and the IR bands. So this coverage extends farther out to maybe 150 days or so. And again, capturing this full evolution is really crucial to really modeling the full SED evolution of these different supernovae. So now that we have our sample and our photometry defined, we can now model the data for each object in our sample using Gaussian process regression, which I'll talk about next. So what is Gaussian process regression? It's essentially a machine learning framework which models the input data as a set of random variables that have a joint Gaussian distribution with some mean and some covariance. This has several advantages. I'm going to talk about the specific advantages for supernovae in a second, but mostly it boils down to the fact that Gaussian process regression doesn't have to assume any parametric form of the data that you're fitting. It naturally provides very robust uncertainty estimates, and it's ideal for modeling time series data. So shown here is an example of a Gaussian process regression fit to some data. I think this is a simulated exoplanet transient or some stellar variability curve, something like that. But the data here is shown in black, and then the Gaussian process fit is shown in blue. And so you can see that the fit does a really good job overall of capturing the sort of semi-periodic nature of the data. And in regions of sort of sparse coverage like here, the fit sort of learns the pattern in the data previously and also extrapolates out some relatively large uncertainties, given that there's no data in this region. So, these reasonable predictions and sensibly sort of large uncertainty regions are really the main advantage of Gaussian process regression. So how this works is that you optimize the hyperparameters of the covariance matrix or kernel that you're using to fit the data. And this is typically done, and in our case, it is done by maximizing some likelihood function by comparing the data to the model predictions. The choice of kernel can enforce certain model behavior. So for example, the fits that I'll show today, we've used an RBF kernel, also called a squared exponential kernel. And this enforces smoothness in the model because it's infinitely differentiable. And the hyperparameters themselves are typically things like length scale, and they set the scale on which the fit can vary. So that's what's being shown here. These three plots show fits to the same data set, but using different choices of kernel length scales, L, and those values of L are sort of shown below each plot here. So you can see that in the bottom left, for example, L is small, and the fit is allowed to vary on much smaller length scales. So you get this sort of bumpier, wigglier fit overall. Compared with the one on the bottom right, this has a much larger length scale, and the fit is more smoothly evolving and more gradual. So by maximizing these kernel hyperparameters, you're able to sort of control the length scale on which your fit models the data. So when this is applied to the photometry of supernovae in particular, there are several main advantages that you get out of this. The first is that Gaussian process regression is very easily extendable to multiple dimensions. And so for our cases, this allows us to fit across both phase and wavelength simultaneously. This is also ideal for modeling sparse data. For example, if you don't have much data in a certain filter, Gaussian process regression, again, can give you very sort of robust uncertainty estimates. You also don't need to assume any physics of the data that you're modeling. So for example, you don't need any prior knowledge about the progenitor properties or the explosion properties of the supernova itself, because you don't want to be biasing your fit one way or another by making these assumptions. For our cases here, in log space, the kernel length scale can typically match the supernova evolution across both phase and wavelength. And by that, I mean that supernovae tend to be faster evolving in bluer filters and at earlier times. So when you log transform both phase and wavelength, those deviations get smoothed out a little bit more. And the kernel length scale can approximate both early time and late time evolution, or blue and red evolution in one kernel estimate. Gaussian process regression can be expensive to run, but for our cases, with our relatively small sample sizes, it can perfectly handle the fitting that we want to do. It can run in several minutes on a laptop with pretty much no optimization. And finally, we're able to apply this uniformly across all of the different supernova subtypes that we're fitting. And this has really never been done before. So Gaussian process regression has been applied in the literature to some supernovae. For example, the plot shown here is an attempt to model the light curves of different stripped envelope supernovae using Gaussian process regression, but applied to all supernova subtypes in one uniform modeling effort. This is the first time that this has been done. And so this brings me to the second part of this talk, which is to discuss our open source code base called GoPro. So this is all publicly accessible on GitHub. I urge you all to check it out if you're interested. We have in this one repository several things. We have the processed photometry of all of the transients in our sample, as well as some metadata about things like their light curve peak, their coordinates, their redshift, and other information. We also have our code, the functionality to perform your own Gaussian process regression on any collection of supernovae that you wish. And finally, we have the final template models that we produce as part of this modeling effort that covers most of the spectroscopic subtypes that I showed earlier. And we also have things like documentation available through Read the Docs. We have example Jupyter notebooks that will walk you through a lot of the modeling steps. So I really want to encourage anyone who's interested in doing similar modeling efforts, either using our data or using data and objects of your own. Feel free to check this out, see if the functionality there can fit your needs. We've really tried to keep this as general as possible to really cover a wide range of use cases. So now I'll walk through some of the steps the code takes to produce these final sort of 3D spectral energy models of different types of transients. So here's an architecture diagram that shows the typical GoPro workflow. And this really consists of three steps. So there's a pre-processing step, which happens first. This is when each object gets fit for its light curve peak, and its data gets transformed into this sort of rudimentary 3D representation of a time-evolving SED. Then there's a data preparation step. The data is split into a normalization set and a training set. And this is needed to do things like calculate photometric residuals that will be the input for the actual fitting, which I'll get to in a second. And then finally, the modeling step is done on the training data. You first optimize the kernel hyperparameters by fitting each object individually. Then once those hyperparameters are optimized, you can then refit each object and obtain this final median template model for the training set's typical SED behavior. So now I'll go through each of these steps in a little bit more detail. So first is the pre-processing step. We first need to estimate a time and a magnitude of peak brightness for each supernova in our sample, because we need to basically set this as a reference point for each object so that we've sort of normalized all objects to the time and the brightness of this peak. So we have an interactive routine to do this for each supernova that's being shown here on the top left. A user can initialize a supernova object and then use this fit for max method by specifying a different filter. The code will then pop up this interactive window, which will show the fit. The fit will be sort of iteratively varied over different phase ranges until it converges on an answer. And then the approximate peak, which is shown here in red, will be returned to the user, and the user can basically say if they like this or if they want to redo the fit. And so all of this information is then saved into a data file that's called the CAT, or the Catalog of Archival Astronomical Transients. So second, we need to construct this sort of rudimentary 3D data cube representation of each object's photometry. And so by that, I mean that we take the photometry and then we transform it into flux units, and we pin each measurement at a specific phase and wavelength, which is being shown here on the left. So this produces this sort of 3D cube representing the rough SED evolution of the supernova. We then need to validate that this is a valid approximation, because I kind of gloss over this fact, but by taking all of the flux in a certain filter and pinning it at a certain wavelength, we're more or less warping the SED of the actual supernova. So to make sure that this approximation is valid, what we do is we essentially interpolate an SED at each epoch, and then we compare the measured photometry with that interpolated SED convolved with the filter functions of the filters that we have data for. And if those two values don't agree within some uncertainty region, we sort of iteratively warp that SED by shifting those flux measurements in wavelength space until those values converge. And then we save those wavelength values to be used in our actual fitting. So it's a bit of a technicality, I guess, but it's one of the necessary steps to validate that our measurements are accurate in representing the actual photometry that we have. Next, for the data preparation step, we need to obtain an estimate of the typical supernova behavior for each class. And this is, again, kind of due to a technicality in how Gaussian process regression fitting works. The math ends up being a lot easier if we assume that the data that we're fitting has a mean of 0. So we can approximate a mean 0 data set by instead fitting the residuals of the photometry rather than the photometry themselves. So to do this, what we do is we take a normalization set, and then we estimate an approximate template using that normalization set. So that's what's being shown here. In this case, we're loading all of the type 2b supernovae. We're aggregating the photometry for each one in our sample. And then for each filter, we're fitting this low order polynomial to approximate a template. And then we subtract off that template from all of the photometry in our sample to get residuals. So here's how we actually create the template models and the code. All of these pre-processing steps have been done beforehand. All of the objects and the data in our public repository already have these steps done. So the only user-facing functionality to generate the new templates are a few pretty easy and straightforward steps. So first you have to initialize a GP3D object, which takes a training set, it takes a kernel, a normalization set, and then a few other parameters like the filters to fit and the phase ranges to fit. And then under the hood, the code calculates all of these residuals for the objects in the training set by using that 3D representation of the supernova shown here on the left, and then subtracting off that approximate template, that polynomial representation shown there on the right. Next, then the kernel hyperparameters get varied and optimized using this GP3D class. So under the hood, this happens by essentially calculating these residuals. That's being shown here on the left. The black points are the residuals, the green points are the actual data, and then that green line is the polynomial approximation. So all of those residuals get fed in to the GP3D object. The code then iteratively fits them to optimize the hyperparameters. And this essentially produces a predicted light curve for all of the photometry that we have for each object, which is shown here on the right. This is an example of a pretty unique supernova called 2016 GKG. This has a really sharp initial light curve peak, as you can kind of see in that inset in the figure. I won't talk too much about the physics of what's actually going on there, but basically we used this as a test case to sort of demonstrate how well our Gaussian process regression performs on these unusual supernovae that might have unique light curves and how well it captures this sort of filter dependency. So you can see here that the early peak is captured quite well by our models. It doesn't have any problem with both the sharp rise to peak and then the sort of gradual, smoother secondary peak. And you can also see that in bands that were missing flux, so for example, the R band over here doesn't have any photometry measurements. Although it has larger uncertainties, the fit more or less matches what you'd expect based on the adjacent fits in, for example, the I band here. So this is a good validation that our fits are performing as expected. And so finally, we produce the final template models by using this GP3D class object to essentially refit each supernova in the training set using our optimized kernel. And this produces this 3D representation of the spectral energy sort of surface. It's a spectral energy distribution at any phase or wavelength. And this is done for each object in the training set. And then all of these individual surfaces are sort of median combined, and that produces our final output template model. So shown here on the right is an example of one of these SED surfaces. Again, this is for a type 2b supernova, and you can see that it has this really early initial peak here, and it captures the sort of smoother secondary peak. And you can also see some of the filter dependency by looking along the wavelength axis here. So for example, the U band flux or the UV is much more sharply evolving and dimmer at late times compared to the redder or infrared flux, which is much smoother and brighter at late times. So now that we have our final output models, we can use them to make some predictions. So for example, we can predict a light curve. This is essentially a slice across this surface at a single wavelength. So that's what's being shown here on the left. This is a predicted light curve from our type 2b template model there. The error bars correspond to 95% confidence intervals. And then we're comparing that predicted light curve with the V-band flux from the supernova 2016 GKG. So you can see that the prediction captures the observed photometry quite well at all times. At really early times, it doesn't quite capture this early peak, but the uncertainty region or the error bars are much larger. And that's because the model has sort of learned that there's more diversity in the light curves of these objects at these early times. Some of them, but not all of them, show this initial peak in the light curve. So we can similarly produce a predicted SED at any phase by now taking a slice that's orthogonal to the slice that we took for the light curve. This is sort of a cut at a single phase. That's what's being shown here on the left. This is a predicted SED at a light curve peak or a phase of 0. And again, you can see that this more or less matches what you'd expect. It's a slightly red. It sort of rises a little bit in the redder wavelengths here, and it's quite dim here in the ultraviolet. That's to be expected. These objects tend to be much more UV dim at around light curve peak. You can also see that the uncertainty region is much larger in the UV. This is because, again, we don't have as much UV data, and the UV data tends to be more diverse in its evolution at these phases. There's also a number of other predictions that one can make using these template models. So all these examples that I'll show have really easy and really straightforward user-facing functionality that's available through the GoPro code, and there's some example notebooks on the repository to walk you through that. So for starters, users can predict photometry at any arbitrary wavelengths or phases that are covered by a model. So that's, for example, shown here. These are something like 5 iterations of predicted photometry in the U, V, and I bands at different phases. What's happening under the hood is that essentially the model is sampling that 3D distribution and its uncertainties to sort of capture the diversity of the brightness at each filter and at each phase. And this can be used for things like building synthetic data sets of different types of transients to inform machine learning classifiers or make predictions. And I'll talk about that a little bit at the end of this talk. You can also use these template models to fit the photometry of a new transient in order to predict its evolution or fill in the gaps at phases that you might not have observed it. So for example, here's just some made up data that I made for a new supernova in the B, V, and I bands, showing this sort of gradual rise to a peak. So you can fit these models to this data and then extrapolate out things like its really early time evolution, which is being shown here. You can see the fits sort of capture the typical behavior that you'd expect. They sort of take a pretty sharp rise at an early time and then a more gradual rise to the light curve peak. And there are substantial uncertainties in early times, again, capturing the diversity and the different light curve shapes for these types of supernovae at these phases. And as a last example, you can use a model to fit the photometry of an existing supernova and then extrapolate out a light curve in a new filter that you might have missed. So even if the object doesn't have any observations in that filter at all. So here's an example of that. This is photometry of another type 2b supernova called 2020 RSC with G and R band observations. And this is fit with the template model for type 2b supernovae. And again, you can see the model does a pretty good job overall at capturing this early peak, as well as the sort of late time, more gradual declining photometry. So now let's say that you wanted to make a prediction of this supernova in the U band. Maybe you missed this supernova with Swift, or you never got U band observations, but you really need some UV flux measurements to constrain things like the physical parameters that you want to infer for this object. So you can take this fit and then using the models, you can extrapolate out a U-band light curve, which is shown here on the right. This was again produced without fitting any U-band photometry at all. And you can see that overall it does a pretty good job of looking like what you'd expect. It captures this early peak, which we see again in the G and the R over here. And then it declines pretty quickly. And like most of these supernovae in the UV, it sort of never reaches a secondary peak and more or less just declines. So the uncertainties are pretty large at late times, but that's sort of to be expected. Again, the UV flux is more diverse after peak, and the G and R band observations also have larger uncertainties due to sparser data at these times. So overall, considering that we didn't fit any U-band photometry at all, this is a pretty adequate extrapolation using these models. And again, these can inform things like having more robust modeling efforts and fitting things like physical parameters and different powering mechanisms or models for some of these transients that have sparse or non-existent light curves in different filters. So for the last 10 or so minutes of this talk, I'll discuss how our template models perform when compared to those in the literature. So first, I'll introduce the work of Kakapach et al. 2024. This has been sort of an inspiration for the GoPro work that we've been doing. So their work built single-dimensional Gaussian process regression templates of different types of stripped envelope supernovae, covering the UV to the infrared. Those templates are shown here on the right. Their data and their modeling methodology is mostly similar to ours. So again, they construct their templates from the UV to the infrared. They have about 165 different supernovae from the classes type 2b, type 1b, 1bn, 1c, and 1c broadline supernovae. And this consists of about 30,000 different observations. And their modeling methodology is very similar to ours. We took this work as an inspiration for what we've done. So, for example, they do things like transform their objects to peak brightness. They calculate residuals using an approximation from a normalization set. And then they use a similar Gaussian process regression framework with a slightly different choice of kernel and likelihood function. Um, However, the main difference between our work and theirs is that their fits are on a filter by filter basis. So they don't capture this sort of multi-dimensional cross-filter behavior, which is sort of the main goal of GoPro. So they compared their templates with some other contemporary templates of other stripped envelope supernovae in the literature, which is being shown here on the right. Their work is shown in the different colored bands compared to these other templates from Drought et al. In the literature in both V band on top and R band on the bottom. So overall, the agreement is quite good around light curve peak. They do notice some differences between the two templates. So for example, theirs extend much farther out to something like 100 days, whereas the drought templates end at like 40 or 50 days or so. And they also notice this disagreement at early times, where their templates tend to be much shallower and slower evolving than the earlier templates showed. And this may suggest that this data-driven modeling, which they undertook, is better suited to capturing the sort of diverse evolution of these objects at early times. Particularly, maybe it's capturing some of these double-peaked light curves that might have been missed previously. So given how well their templates performed, we wanted to compare our own predictions with their templates. In particular, our samples have quite a bit of overlap, so we're able to do a sort of apples to apples comparison by comparing the predictions from each model to the actual observed photometry for objects in both samples. And so we can quantify the amount of sort of deviations between the models and the observations themselves in a per filter basis. So the results of that analysis are shown here in these two bar charts. On the left here, we're showing the median of the mean absolute deviation, or MAD, per filter. And then on the right here, we're showing the median reduced chi-squared per filter per object. So the left here, the MAD, this sort of quantifies how much on average the two models deviate from the observed photometry. And the chi-squared on the right is more of a measurement of goodness of fit and is more sensitive to outliers. So we overall notice very similar behavior between the two models. There really isn't much discrepancy at all between either the MAD measurements or the chi-squared measurements. The UV filters tend to have larger deviations. Again, that's more or less to be expected. The UV is less well sampled, and it tends to have more diverse evolution. So overall, this is a good confirmation that the templates that we've produced are accurately fitting and reproducing the typical transient evolution. We also did a similar comparison using these type 1 superluminous supernovae templates in the literature. This is work done by Gomez et al. They built the first templates of type 1 superluminous supernovae, which are shown here on the right. So similarly, they fit between the UV and the infrared. Their sample consists of more than 260 superluminous supernovae with over 300 or over 30,000 detections. And however, their modeling methodology differs from ours a bit. So they fit each of the objects in their sample with these physically motivated powering mechanism models. I believe it was radioactive decay plus a magnetar spin down model. And then they interpolated between those fits for each object and each filter to produce those final 3D templates that are shown here on the right. So the templates themselves are still data driven, but they rely more on physical assumptions and modeling than the work that we do for GoPro. So here I'm showing the results of a similar analysis comparing the median MAD and those median reduced chi-square values for each object in the overlap of our two samples. And here you can see that GoPro consistently matches the observed photometry of these superluminous supernovae better than the sort of physically motivated models from the literature. So what I'm not showing here is that this is mostly caused by substantial deviations between the literature models and the observations at really early times, which may indicate that the nickel plus magnetar model doesn't fully capture the diversity and the powering of these objects at early times. And so once again, this shows the advantage of using this data-driven modeling, which we're undertaking here, because we're not tied to any physical assumptions that might be biasing our fits. So we can also use our templates to gauge how accurate different synthetic photometry datasets are. So for example, we've compared with the elastic dataset. For those of you who may not be as familiar, elastic was a challenge that simulated different LST light curves for millions of transients, sort of to prepare machine learning classifiers and other things for LSST. So these were all simulated at a realistic range of redshifts for the supernovae that LSST will discover. At the time, these were all streamed publicly over different brokers and alert streams, but now their full light curves and their classifications are all publicly available. So we're motivated to do this comparison, again, by the work of Kakbash et al., because they found significant deviations between their own templates and the elastic dataset, which is shown here on the right for 4 different filters. Their templates are shown in green. The sort of median per day elastic data set is shown in pink, and then each individual supernova that elastic predicted is shown in black. So the per day median more or less matches the template predictions, but you can see there's much more spread or deviation in the total distribution of the synthetic photometry. And this suggests that the elastic simulation may have overrepresented the diversity in these supernova light curves for a given class. In this case, these are stripped envelope supernovae. However, it's difficult to make concrete conclusions about this because of the sort of redshift nature of the elastic simulation, and because the Kakbash templates were produced with mostly low redshift supernovae, it's more difficult to sort of redshift those and compare to the elastic dataset. So this is where GoPro can come in. Because we model the full time evolving SED, we're able to more easily predict and compare between the evolution of the elastic transients in their own rest frame. So that's what we did. In short, we compared how much the elastic transients deviated from our own template models in each transient's rest frame. So here I'm showing the results for type 2 supernovae. Previously, there was a hint of a discrepancy for stripped envelope supernovae, and we wanted to test if that discrepancy also extended to other classes. So in short, it appears that it does. The left plot shows the median residuals between our GoPro templates and the elastic photometry in 4 different filters. And you can see that in general, the elastic photometry is biased by about 0.5 to 1 magnitude across all filters in the negative direction. So it predicts fainter evolution than our models show. And then the 95% confidence intervals, which are shown by sort of the whiskers on this box and whisker plot, extend all the way out to something like plus or minus 1 or 2 magnitudes in each filter. And the right shows the reduced chi-squared between our own models and the elastic measurements. The chi-square values aren't too bad, but some objects do show substantial deviations. And finally, we can validate that our model predictions are accurate using left-out photometry. So to do this, we turn to the ZTF Bright Transient Survey. This is a brightness-limited sample of spectroscopically classified supernovae. It's something like 75% complete down to 19th magnitude. It currently consists of over 7,000 supernovae, the breakdown of which is shown here by these different pie charts. They have very good coverage of all of the major subtypes that we have in GoPro, so it makes this comparison easier. And because these are mostly nearby objects, due to the brightness limited nature of this survey, they tend to be observed with Swift more often, and so there's substantial overlap with our own sample, which means that we can use left-out photometry from objects in our sample to validate our template predictions. So we're essentially curious to see how well our models can predict missing photometry. In order to quantify this, we choose observations or objects that are in the overlap of our sample and the Bright Transient Survey sample that have both Swift UV as well as G, R, and I band photometry. So what we do is we fit these supernovae using the template models of that class in only the optical G, R, and I bands. And then we use those fits to extrapolate out a left out UV light curve. That's being shown here on the right. This is a type 2 supernova. We only fit the G, R, and I bands, and then we predict a U band light curve shown here in purple. The light curve looks reasonable, but we want to compare to the actual photometry that was taken for this object to see how off our predictions are. And it turns out that for the most part, we actually aren't too far off at all. These are histograms showing the distribution of the residuals. It's the actual photometry minus the GOPREAUX predictions for these type 2 supernovae in both the UVM2, and UVW1 bands. So all of these distributions have a median very close to zero. This indicates that the majority of the objects have relatively small differences between the naive predictions that we're making and the actual measurements themselves. The standard deviations are all around a magnitude or so, which typically isn't great, but given that this can be applied to predict missing flux and then fold those into uncertainty estimates of physical parameters or bolometric luminosities, this will enable more statistically robust estimates of these parameters. So in my last slide, I'll just discuss some future steps and future work. Now that we've developed and validated these models, there's a number of different physically motivated avenues for further research. So we are actively integrating GoPro light curve templates into the light curve links light curve simulator package. This will be used to predict things like LST light curves for different types of supernovae. This is an easy to use package, and the GoPro implementation is really seamless. So hopefully users can very easily simulate light curves that pull from our own templates. These templates can also be used to generate synthetic data to inform different machine learning classifiers in the future. We can also develop things like an outlier classification or identification framework, in which sort of like deviations between the predictions and the observations over time can identify peculiar supernovae relative to their spectroscopic type. And this may indicate things like different powering sources or progenitors for those objects. We're also calculating bolometric light curves by integrating over the 3D SED surface itself, and we can quantify typical bolometric corrections for different classes of objects that might have left out UV or infrared photometry. And then finally, the predictions and the measurements can enable more robust physical parameter inferences using the uncertainties that are derived from our models. So just to conclude, GoPro is this package that contains open source photometry that's uniformly processed for 1,300 transients, very user-friendly functionality to model the time-evolving SEDs of different transients using Gaussian process regression, as well as these final 3D spectrophotometric template models for predictions, simulations, and physical parameter inferences uniformly across all different supernova subtypes. So this is an active software package that's being developed by myself and different members of the Metal Group at the University of Virginia. If anyone has any suggestions or feature requests, please feel free to reach out. I'm very happy to hear them. Also, check out the code. This is a QR code that will take you to the GitHub page, and I'm happy to take any questions. Thank you.
Thank you, Craig. And ask any questions by raising your hand here, typing them in chat, or posting on the Slack channel. Postia, go ahead.
Craig, really nice talk. I actually have a lot of questions, so I should pick one, I think. So when you are doing Gaussian processes with S-bands, how do you encode S-band transmission information? So how do you like use? So I understand when you already have template, it's easy. You could just integrate over passband, right? But if you have like band fluxes, right? How do you train continuous 3D model on them or 2D?
Yeah. Yeah, so this is where some of the let me see if I can go back to that slide. Some of these sort of strange pre-processing steps that we have to take come in. So we essentially validate that that our flux measurements, which we more or less naively pin at a single wavelength, match the true flux measurements from the filter passbands and from the supernova SED. This is a pre-processing step that we take to essentially change the wavelength at which we pin this flux to do this validation. So yeah, it is a weird sort of technicality of how we're doing our pre-processing. But essentially, it's for this exact reason that to take into account the things like, especially for the Swift UV filters, which have this substantial red leak, We have to, instead of just pinning the flux at like the central wavelength of each filter or each passband, we have to be a little bit more accurate in ensuring that the sort of SED that we're fitting is representative of the supernova itself. Does that make sense?
I could imagine that you could like change Gaussian process target optimization function and actually do passband calculation, right, on each
Yeah.
like parameter estimate. Is it just too expensive to
Yeah,
do?
yeah, I think so. Yeah, so this process, this iterative process of essentially assembling this data cube is quite expensive already. Given the samples of the transients and the number of data points that we have. I haven't tried integrating it into the actual like likelihood function. But that's an interesting idea that might be worth checking out. Yeah. Yeah, I can't say off the top
Okay,
of my head how
thank you.
expensive it would be, but yeah, it's interesting. Yeah, thanks for that.
Oh, thank you. Okay.
We have a question in the chat about GP regression. Does the model encode some kind of assumption that data points that are close together in time are likely to have values that are also close together? Is there any explicit modeling of the frequency ranges that can be present in a signal, or is that implicit in the covariance?
Yeah, yeah. So it's explicit in the covariance, exactly. Yeah. So this is where the idea of these kernel length scales come in. Essentially, what that means is that data points that are closer together in either phase or wavelength are tend to be more covariant. So this is sort of the idea of how we can use data in one filter to predict the light curve in an adjacent filter. Um, those predictions get worse, or I guess the uncertainties probably get larger the sort of farther away you go in either phase or wavelength, which is why, let's see if I can find a good example. Um, but things like this object, for example, out here where there's really no photometry, um, these error bars get much larger. The the model has still learned the typical behavior from both the sort of normalization set that we use to calculate the residuals, as well as the sort of interfilter dependency and the optimized kernel. But you can see that like the when the length gets larger in either phase or wavelength, the predictions get more uncertain, essentially. Yeah.
Um, Heather says, thank you so much. Okay, I see another hand. Fantastic. Alexandra, or I'm so sorry, Alessandra. Take it away.
Hi, I wanted to ask, how do you treat or consider upper limits?
Yeah, that's a good question. So this is an advantage of doing our fitting in flux space where we can take advantage of upper limits or non-detections in flux measurements. It's a little bit tricky to do so. We This could probably also be folded into the actual Gaussian process regression itself. But what we do to approximate it is essentially um, use the non-detections or use the upper limits as almost like detections with a very small uncertainty to make the fits sort of respect those more. So that's what in some of these examples, for example, possibly here, is what's driving the this like late time or early time behavior, I guess, to very low flux levels. We have some non-detection here, which just isn't being plotted, but the fits are respecting it essentially, which is driving down the fit in that area. If that makes sense.
Thanks.
I had a question about how you handle the data provenance with, I think it was the cat phase with the 1300 transients. Did you process them all at once, or has this been like iterative?
Yeah, yeah. So it took a while. So it was more or less iterative over, I don't know, a year or so. So we relied a lot on things like the force photometry servers from different surveys like ZTF or Atlas or Assassin, which have nice, like APIs or user-facing functionality to do a lot of that more or less automatically. For Swift, we wrote sort of a custom implementation of the SUSE pipeline, which was developed by Peter Brown to process Swift photometry. This ran with, I would say, semi-automatically. it took some user inputs, but it did things like searching for template observations to do background subtraction more or less automatically. And so it was a bit of an iterative process to get the sample processed. We had to set a sort of hard cutoff of like this date where we would stop processing data for new objects and just kind of like use the data that we already had. But we're also open to taking new data into our repository through things like pull requests on GitHub and things of that nature too.
Thanks. All right. Thank you so much, Craig. It was a fantastic talk, and thank you for everyone for attending the talk series today. Our next talk is going to be August 13th. Stay tuned for an announcement. We'll be hearing about the light curve package from Kostya Milanchev. And in the interim, please join the LSST-DA Link Tech Talks Slack channel or the link at list.lsst.org mailing list for more information and future announcements. And we have links on our Discovery Alliance website as well. We hold office hours every Thursday at this time slot, except when it conflicts with the Tech Talk series. If you have an idea for a Tech Talk, we'd love to hear from you. Feel free to reach out to us on Slack or via email listed on the Tech Talk webpage. And with Craig's permission, today's Tech Talk will be available on our YouTube channel within the next few days. Have a great rest of your day or night. Thank you so much.
Thank you.